Hello everyone. In this video, let me concentrate on width of the principal maxima in a single slit Fraunhofer diffraction. So you already know this. When the single slit is introduced, you will get the principal maxima like this, and then secondary maximas like this. So if this is the screen and this is the intensity pattern I am getting, see at this point this is the first angle at which the secondary minima forms, and on either side I will get this is also same theta for which the secondary minima forms. So up to that central maxima spreads, we can think on like that. Up to secondary minima on either side the central maxima spreads. So if I join, so this is known as the angular width of the central maxima. Okay, and if you consider this length on the screen, that is known as, if you call from here to here as y and here to here as y, then 2y is called linear width of the central maxima. Okay, you know that for which theta for which the first minima exist on either side is given by condition for minima is E sin theta is equal to m lambda. We have derived this, correct? But this is the first minima, therefore m is equal to 1 I can write. So this will be E sin theta is equal to 1 lambda, or sin theta can be written as lambda by v. Since theta is very small, I can write sin theta approximately equal to theta. Therefore I will get theta is equal to lambda by E. So angular width means angular width w theta is represented as, this is 2 theta, just now only we have seen on either side. Therefore 2 theta can be written as 2 into lambda by E. This is the central angular width of the central maxima or principal maxima. Also from the figure, see if I call the distance from slit to screen as d, then what is tan theta? Tan theta is equal to opposite by adjacent. Therefore I can write this as y by d. So from the figure, tan theta can be written as y by d. So if the lens is very close to the slit and far away from the screen, then d is approximately equal to f. See, we have to introduce one lens here to get the intensity pattern. If this lens is very close to the slit and very far away from the screen, then d is nothing but the principal focal length of that lens. Therefore I have replaced d by f in the tan theta expression. Okay, therefore here also, since theta is very small, tan theta can be written as theta. You know that theta can be written as sin theta, for theta is very small. Therefore if you replace tan theta as by the expression sin theta, so sin theta can be written as lambda by E. So if I use that, I will get lambda by E is equal to y by f, or y is equal to lambda f by E. This is just a y. If you want the linear width is 2y. Therefore I can write w is equal to 2 lambda f by v. I will call this as equation number 2. So from 1 and 2 I can write linear width is equal to angular width into f, because 2 lambda by e is nothing but angular width into f is the focal length of the lens used. So this is the expression for the width of the central maximum, both in the case of linear and in the case of angular, and the relation is also given. Okay, and you can observe two more points here. See, angular width is directly proportional to lambda. So if I use the red light for a diffraction, then I will get more central width than for the violet, because for violet the wavelength is less. Okay, this is first point you should remember. They may ask you these points for 2 marks question or conceptual question. Why in the Fraunhofer diffraction central maxima is very less for violet light than the red light? Then you have to use this expression and you have to explain. And second thing I can observe is W is inversely proportional to 1 by E. That means the slit width increases, the central maxima width decreases. Or in other words, central maxima increases for narrower slit. So more the narrow slit, ಎಷ್ಟು ಚಿಕ್ಕ ಸ್ಲಿಟ್ ಯೂಸ್ ಮಾಡ್ತೀರೋ ಅಷ್ಟು ಚೆನ್ನಾಗಿ ಡಿಫ್ರಾಕ್ಷನ್ ಪ್ಯಾಟ್ರನ್ ಬರುತ್ತೆ ನಿಮಗೆ. This is the meaning of this. as the slit becomes very narrow, then the central maxima width is very high and the diffraction pattern is beautiful. Okay, and now from the same point, if the a value increases to very large compared to the lambda value, that means e is very large compared to the lambdas, then what happens, this ratio is very less. As this ratio is very less, w is also very less, correct? That means the width of the central maxima as well as the other maxima, secondary maxima, also decreases, so that there will be a overlapping. The central maxima comes very nearer to the secondary maximas, so they will overlap, and you cannot observe that unobservable diffraction pattern, and it looks like a rectilinear propagation. That is why for the diffraction to observe, the slit will be very narrower. ಅರ್ಥ ಆಗ್ತಿದೆಯಾ? ನಿಮ್ಮ ಆರ್ಡಿನರಿ ನಿಮ್ಮ ಕಿಟಕಿನಲ್ಲಿ ಅಲ್ಲೆಲ್ಲ ನೋಡಿಬಿಟ್ರೆ ನಿಮಗೆ ಮನೆಯಲ್ಲಿ ಏನು ಕಾಣಿಸುತ್ತೆ? ನಿಮಗೆ ಆರ್ಡಿನರಿ ರೆಕ್ಟಿಲಿನಿಯರ್ ಪ್ರೊಪಗೇಷನ್ ಇದೆ ಅನ್ನೋಂಗೆ ಕಾಣಿಸುತ್ತೆ. ಅಲ್ಲಿ ಮಧ್ಯೆ ಏನಾದರೂ ಒಂದು ವಸ್ತು ಇಟ್ಟರೆ ಯು ವಿಲ್ ಗೆಟ್ ದ ಶ್ಯಾಡೋ, ಕ್ಲಿಯರ್ ಶ್ಯಾಡೋ ಯು ವಿಲ್ ಗೆಟ್. You won't get any encroachment of light into the region of geometrical shadow. That is diffraction you won't observe. For the diffraction to observe, the slit must be, the aperture must be very small. And that is why we will say, what is the condition for diffraction? The slit width must be comparable with the wavelength of the lambda. ನೋಡಿ ಇಲ್ಲಿ one more fourth thing you have to observe, as a becomes equal to lambda, comparable with the lambda ಅಂತ ಹೇಳಿದೀವಿ, ಬಟ್ ಈಕ್ವಲ್ ಟುನು ಇರಬಾರ್ದು, ಅದಕ್ಕಿಂತ ಜಾಸ್ತಿ ಕಡಿಮೆ ಇರಬೇಕು. ವೇವ್ಲೆಂತ್ಗಿಂತ ಸ್ಲಿಟ್ ವಿಡ್ತು ತುಂಬ ಕಡಿಮೆ ಇರಬೇಕು. ಅಕಸ್ಮಾತ್ ಈಕ್ವಲ್ ಟು ಲ್ಯಾಂಬ್ಡಾ ಆದ್ರೂ ಎ ಈಸ್ ಹಿಯರ್ slit width, I can write a is nothing but e. A and e both are same. In some textbooks they will take slit width as a, in some textbook they will take slit width as e. Okay, anyway, when slit width is equal to the lambda, then from the expression sin theta is equal to lambda by e, then I will get a by a is equal to 1. Therefore, theta becomes equal to 90 degree. That means if the slit is here, the central maxima covers the whole thing, correct? Because theta is not now this much, theta is now 90 degree, correct? And also the last note I can take from this side is, see, you know the expression lambda by e is equal to y by f. Sorry, lambda by e is equal to y by d, correct? 1 minute. F I have replaced when the screen is very nearer, otherwise I have to write in general this as d, correct? Therefore lambda by e is equal to y by d, or d is equal to e by e into y by lambda. That means, so there is a particular distance between the slit and the screen for which exactly equal to the slit width there is a central maxima width is exactly equal to that slit width. You will get the width of the central maxima, and then your secondary maximas will come. That means width of the central maxima is exactly equal to the width of the slit. In that case, whatever the distance between the slit and the screen is there, and that distance is known as Fresnel's distance, df. Remember, okay? So that is what I have given here. We know that d is equal to e y by e y by lambda. So the distance from slit to screen at which the spreading due to diffraction is exactly equal to slit width is called Fresnel's distance, and you can call that as, at that point, y is equal to e. That means width of the central maxima is equal to e. Then I can write df is equal to e into e by lambda. You will get e square by lambda. This is known as Fresnel's distance. So they may ask you this also, define Fresnel's distance and what is the expression for this. Okay, you can derive the expression like this. Next, we have concentrated on the diffraction due to the single slit. Now we will be concentrating on the diffraction due to many slits. If there are many slits are there, then what happens to the diffraction pattern? And that many slit arrangement is known as diffraction grating. So what do you mean by diffraction grating? It is an arrangement of many slits with equal slit width and equal opaque width is known as diffraction grating. See, what do you mean by opaque width? If you are considering like this, so this is your slits. This portion is your slit. That means here the light will allow. And here again opaque region. Again here the light is allowed. Opaque region. Light is allowed. So this is known as opaque width. And this is known as slit width. So slit width will be should be equal in any grating. You cannot imagine first slit width is very less and then you will get a larger and then you will get a still more larger. No, you cannot imagine like that. Slit width should be equal and opaque width should be equal, and such an arrangement is known as diffraction grating. See, like your lens, like your mirrors, like your prisms, we can also prepare this type of gratings. This type of gratings is also known as diffraction grating or transmission grating. Grating experiment is also there in your practicals. Once we do that, at that time I will explain. Anyway, how to prepare the grating? It is constructed by ruling equidistant parallel lines with a fine diamond point on the glass plate. Take a glass plate with a fine diamond point, make the rulings. Where the rulings are there, that becomes the opaque point and the other region become a slit point. Are you getting the idea? So these are the opaque points and this is the slit point. So anyway, this is the slit width or the transmission region and this is the opaque region. Transmission region, opaque region, transmission region, opaque region. So in this way it forms a many number of slits, and this type of arrangement is known as diffraction grating. The ruled lines are opaque to light is called opacities, and space between any two lines is transparent to light. That means it will allow the light, that is known as transparencies. So that is why this type of grating is known as transmission grating. And there is also one more grating. Instead of taking the glass plate, if you take a silvered glass plate, that means silvered glass plate is nothing but your mirrors. So you can observe, mirrors means you have taken your glass plate and on one side it is silverized, then it will be converted into a mirror. Instead of doing this experiment on simple glass plate, if you do the same experiment on silverized glass plate, then you will get a grating, and such a grating is known as reflection grating. Anyway, that is not needed. I am just explaining for the sake of you. So anyway, we will be concentrating on the transmission grating. And also observe one more point. There are 5,000 to 12,000 lines per centimeter of grating. Just imagine. So if you take a per centimeter of glass plate or per centimeter of grating, within that there will be a 5,000 to 12,000 lines which is made by a sharp diamond point. You should imagine this, how they will construct this transmission gratings. Anyway, in general, if you take a virtual view, I can write like this. See, if I place the glass plate like this, some point there will be no allowing of light, that points are known as opacities, and some point there will be allowing of light and that acts like a slits, and that is known as transmissions. So if the, and you know that all the opacities should be of equal length, if I call that width as B, and all the transmissions should of equal width, if I call that as A, then from one slit to another slit, what is the distance? That will be equal to A plus B. So if this is the first slit point, see, from point to point you cannot take from here to here. Slit means if this is the starting point of the slit, here also you should take the starting point of the second slit. Then from here to here, the total distance will be A plus B. Here to here, this is A, and this is opacity's width, that is B. Totally the distance between first slit to second slit will be A plus B. Therefore A plus B is it's a distance between two successive slits, and that is also known as grating element. Remember this. So these are the 3 note point you should remember about the diffraction grating. Now let me concentrate on how the grating works and what is the intensity pattern due to grating, that is due to many slits. See, you already know this. If the single slit is considered, how I can write, this is for many slits, and the middle point of the slit region I will call that as S1. Similarly for second slit S2, similarly for S3, like that I can write up to n slits. As usual, when theta is 0, you will get the central maximum. As passed through the lens, you will get the O point as central maximum. For any other theta, you will get a another point. Whether that point is minima or secondary maxima, that will be decided on some condition. So this is the experimental or the line ray diagram arrangement for the grating experiment. Okay, you know that you should observe very carefully here. If you consider a single slit here, the slit point is considered as according to Huygens principle, at all the points you will get a secondary waves, and those secondary waves meet on the screen. So this is for the within the single width I have did. Now you have to consider those arrangement for each and every slit. So S1 will also give some net amplitude, S2 will also give some net amplitude, S3 will also give net amplitude, and those net amplitude again reinforce or again interfere to form a diffraction pattern. You should observe very carefully. And from the single slit diffraction we have obtained this, the net amplitude for single slit. In the single slit experiment we have obtained this experiment. You can cross check with your notes. A sin alpha by alpha, where alpha value is pi a sin theta by lambda. Observe here, there I have taken E as the slit width notation, so I have written here pi e sin theta by lambda, but here I am changing the slit width as A, therefore I have replaced E with A, therefore I will get pi a sin theta by lambda. Let me consider, see here you have to imagine two types. One is within the slit there are n secondary waves are coming. They will reinforce to give the net amplitude of A sin alpha by alpha. Now this also give A sin alpha by alpha, this also give A sin alpha by alpha, this also give A sin alpha by alpha. Similarly there are n slits are there. Now again these A sin alphas reinforce to give the net diffraction pattern. Understood? So if I consider two slits at a time, actually I have to take total n slits. Let me consider if I take two slits at a time. So this is the first slit and this is second slit. So what is the path difference? Path difference can be represented by writing a perpendicular. So S1n is the perpendicular. So from triangle S1n S2, I can write sin theta is equal to S2n by S1 S2. So S2n is equal to S1 S2, that is distance between slit S1 and slit 2 is nothing but A plus B into sin theta I will get. But this S2n is nothing but the path difference between the two secondary waves coming from the slit S1 and coming from the slit S2. Okay, therefore that can be written as path difference can be written as A plus B into sin theta. Let the phase difference between these two secondary waves coming from S1 and S2 be phi anta itkolana. Let it be phi. So then how can I write the resultant? If two waves are there, how they will combine with a path difference of pi? Like your amplitude is a vector quantity. So according to your vector quantity, how to find the resultant? A square plus B square plus 2AB cos theta. Theta is the angle between two vectors. So here phi is the phase difference. That means this is the angle between the two amplitude vectors. Therefore I can write like this: A sin alpha by alpha whole square, A sin alpha by alpha whole square, 2 into A sin alpha by alpha, A sin alpha by alpha into cos pi I can write. If I simplify, I will get, this is 2A square sin square alpha by alpha square plus again inside this also 2A square sin square alpha by alpha square into cos pi. So from these two, this term is common. So if I take that term out, then I will get 1 plus cos phi is the remaining term. 1 plus cos phi can be written as 2 into cos square phi by 2. So, if I call phi by 2 as beta, then I can write phi is equal to 2 beta. So, if I know the phase difference phi, then I can find the path difference. So, phase difference is equal to 2 pi by lambda into path difference, that is 2 pi by lambda into path difference. Just now we have derived a plus b sin theta. Therefore, I will get, see, this phase difference phi is nothing but 2 beta. Just now we have proved. Therefore, beta is equal to pi by lambda into a plus b sin theta. See, this is for it just two situations I am finding. But imagine there are n many number of slits are there, so I have to take for n number of slits. So for n number of slits I cannot go on like this, so I have to use the formula. You already know this from the simple harmonic motion. You have arrived this expression before starting the single slit. So net amplitude will be R is equal to A sin n phi by 2 into sin phi by 2. When this is proved, when there are n number of simple harmonic waves, each of amplitude A, correct, then the net amplitude at the screen is given by A into sin n phi by 2 into sin phi by 2, and each having the phase difference of phi. The correspond to any two successive waves are having the phase difference of phi, then I can write like this, correct. Now if I am having n number of waves, small n number of waves, I can write like this. If I am having capital N number of waves, because there are n slits, capital N number of slits, okay, I am applying the same formula for grating. Observe very carefully. Now also the phase difference between any two successive waves is phi only. Therefore, I can write like this. But what is the amplitude of each wave within the slit? That is A sin alpha by alpha, capital A sin alpha by alpha. This is the amplitude. So replace your small a with this, and phi is same thing, but n with small n with capital N. Then what will be your net amplitude for grating? R is equal to A sin alpha by alpha, correct, into sin capital N phi by 2 whole divided by sin phi by 2, correct. But phi can be written as 2 beta. Just now we have proved. So I can also, if I replace phi with 2 beta, 2 and 2 get cancelled. Then I can write sin n beta by sin beta. So this is the net amplitude due to n number of slits. That is what I have used here. See, the situation will between first and second slit will be same as the second and third slit. That means between second and third slit also there is a phase difference of phi, and net amplitude in the second slit is also A sin alpha by alpha. Net amplitude in the third slit is also A sin alpha by alpha, by using the condition of single slit condition if I use. Okay. And we have just proved phi is equal to 2 beta. So if I use that idea here, then I can write here the net amplitude as R is equal to A sin alpha by alpha into sin n beta by beta, and therefore intensity can be written as A square sin square alpha by alpha square into sin square n beta by sin square beta. So this is the amplitude and intensity when the grating is used, that is when there are many number of slits are there, n number of slits are there. Now again I can find the condition for principal maxima and condition for minima and condition for secondary maxima by using n number of slits. That is what I am doing here. Condition for principal or central maxima. See, the very one simple thing I can guess here is, since I should be maximum, that is I becomes infinity when this sin beta is 0, correct. When the denominator term is 0, then the numerator term becomes infinity, correct. So one simple guess, general guess I can do is intensity is maximum when sin beta is equal to 0. So if sin beta is equal to 0, then beta must be, angle must be plus or minus n pi, where n can take any values from 0, 1, 2, 3, etc. So but if I substitute this beta value directly, then it will take indeterminate form, because sin n beta divided by sin beta, n can be written as plus or minus n pi, and here also plus or minus n pi. So this value is also 0, this value is also 0 by 0 form is indeterminate form. So I have to remove this indeterminate form by applying the limit. So limit, now beta value taken to be tends to plus or minus n pi. So for this no formula is there, but limit theta tends to 0 of sin theta by theta is value is there, but sin n theta by sin theta no value is there, so I cannot use this formula. This is 1, correct? So I cannot use this formula, so I have to remove this limit by applying some other method. So in the mathematics there is one L'Hospital's rules. I don't know whether you are aware of this or not. For the time sake you should remember like this. From L'Hospital's rule, the limit will continue when the determinant is taken for both numerator and denominator with respect to the angle. Therefore I can continue the same limit, beta tends to plus or minus n pi. Now I will take the differentiation d by d beta of sin n beta and d by d beta of sin beta. Why I am doing all this circus? Because I have to remove the limit. Directly I cannot remove the limit. Okay. Now a differentiation of this can be written as n cos n beta. Will you agree? And in the denominator you will get cos beta. Now if I apply the limit, then I will get n cos n plus or minus n pi in the place of beta plus or minus n pi, and here also cos plus or minus n pi. What is cos n pi value? Is 1. And similarly cos plus or minus n pi value is also 1. Therefore finally I will get this, for this term sin n beta by beta term I will get n value after applying the limit. So what is the final expression, remaining expression for intensity? I is equal to, the first term remains as it is, a square sin square alpha by alpha into I will get n square. Why I am getting n square? Because in the intensity term this is sin n beta by beta whole square I can write, correct? I have rate taken only for sin n beta by beta, but in the intensity term the square is there. Therefore I can write the final result square, n square. Okay. So this is the intensity for the principal maxima. Remember this. So there are no one principal maxima here. So there are many principal maxima. Why? Because we know that beta value taken to be plus or minus n pi. Beta, we have derived the expression for beta, that is pi by lambda into a plus b sin theta, that is plus or minus n pi. I can write pi get cancels. So I will get finally a plus b sin theta is equal to plus or minus n lambda, where n can take any values from 0, 1, 2, 3, etc. So n equals 0 corresponds to the 0 order principal maxima. So here there are so many principal maximas are there, correct? So n equals 0 is called 0 order principal maxima. N equals 1 first order principal maxima. Similarly n can take minus 1 also. That means on either side of the 0 order principal maxima there will be first order principal maxima, and similarly there will be plus 2 and minus 2 here, that is second order principal maxima on either side of the 0. Such see, so that means there are so many principal maximas are there in diffraction grating. Remember this. Okay. And also you can derive the expression for, next we have to derive the expression for condition for minima. This I will continue in the next class.